Hello everyone. The paper we will discuss today is overview of the spark physics, basis towards the exploration of burning plasma regimes in high-field compact tokamaks. If you have any questions, I'd be happy to hear your comments. Section 3. Main scenarios. For the initial scoping of tokamak scenarios and machine parameters, a conservative, empirical-based power balance approach has been taken. This method is inspired by standard plasma operation counter popcorn analysis and has been improved to account for refined treatment of radiation from impurity ions and corrections to scaling laws for peaking and power threshold. Among other aspects, Figure 1b shows the nominal popcorn plot for SPARC with the machine parameters indicated in Table 1. Within plasma physics and machine limits, a large operational space is found that exceeds the mission requirement Q bigger than 2, with a maximum of Q equal 11 when operated with a 50-50 mixture of DT. For baseline performance predictions, a dilution of main ions of N dt per Ne equals 0.85 are assumed, as well as an effective ion charge of Z equal 1.5, as described in 7.11. A nominal concentration of tungsten of N per N, Nw per Ne equal 1.5 times 10 to the minus 5 powers is employed, consistent with what has been achieved in other tungsten world machines. This scenario, which will be referred to as the primary reference discharge (PRD), operates with a volume averaged density of Ne equal 3.1 times 10 to the 12 powers per meter cube. Substantially below the green wall limits, Nz equal 8.4 times 10 to the 20 powers per meter cube, and low beta N equal 1.05. An energy confinement time of Te equal 0.77 second is estimated from the ITPA T scaling law, with an H factor of H equal 1.0. The PRD requires only 11.1 megawatt of ICRF input power, as alpha heating keeps the energy flows above the estimated LH threshold power. This scenario produces 140 megawatt of fusion power and all tokamaks systems are being designed to sustain this power level during a 10-second current flat top, including the effect of neutron heating and corresponding requirements for shielding and cooling of the superconducting magnets. While the PRD scenario employ satisfies the SPARC mission, and it has been the discharge that has largely driven the design, as it generally represents the most demanding implications for various engineering systems. There is a number of other scenarios of interest for physics studies and that will be used to build expertise towards the Q bigger than 2 milestone. Investigate specific physics topics or be used as contingency pathways to achieve break-even. The large margin that the PRD scenario has with respect to the Q bigger than 2 mission means that there is significant contingency in case of degraded confinement or pedestal performance. In fact, operation with a degraded H mode confinement factor of H equals 0.7, two standard deviations below the database fit, still fulfills the Q bigger than 2 mission. Similarly, operation at 12.2 Tesla, but with L mode confinement H equals 1.0, can also achieve Q bigger than 2 owing to the potential of running at lower density Ne equals 1.4 times 10 to the 12 powers per meter cube and high input power P equals 21.1 megawatt, a condition with unlikely to result in H mode due to power requirements associated with the low density branch of the LH power threshold curve. Even in the case that H mode is accessible in these conditions, it can be avoided by running in unfavorable grad B drift using upper single null geometries or by controlling P SOL smaller than PLH through core impurity seeding. Plasma with lower area elongation K equals 1.65 with a single null equilibrium are also possible and significantly less demanding for the vertical stability control system and colloidal field coil set. Such scenario is also expected to achieve Q equals 6.5 Likewise, the toroidal field coil set can also allow the exploration of scenarios with slightly larger inner and outer gaps, 3 cm versus 1 cm in PRD, by decreasing mirror radius to A equal 55 cm. Scenarios at reduced magnetic field may also be of use to the SPARC program. In particular, scenarios with BT equal 8.0 Tesla are easily accessible because the ICRF frequency of 112 MHz is resonant near axis in plasmas with H minority. Also, such a scenario only achieves Q equal 1.6 in H mode with the assumptions used here. Shifting the resonance location to slightly off axis using BT equal 8.6 Tesla is expected to increase performance enough to reach Q bigger than 2 under the same assumptions for the kink safety factor. Thus, at slightly higher plasma current, this will allow the study of possible fast ion turbulence stabilization effects with off-axis heating of minority populations as well as high Z impurity control plasmas with BT equal 8.0 Tesla are also anticipated for early operation with deuterium-only plasma, as will be discussed in the next section. Given the high power requirements for H-mode access at BT equal 12.2 Tesla in DD, operation with 8 Tesla will be needed to study H-mode physics, pedestal formation, and transients for introducing tritium in the machine. Figure 1c presents some characteristic separatrix shapes that the toroidal field coil set is able to produce for SPARC. Thank you for listening to the end of today's show.